Hello and welcome to 6.3. Today we're going to look at logs and their properties. If you recall from section 6.1 when we were talking about exponential functions, we said that exponential functions were one-to-one, meaning that they passed a horizontal line test. So what that horizontal line test tells us then is that exponential function has an inverse. Well, today we're going to look at that inverse because that inverse is called a log or a logarithmic function, and that logarithmic function has a base of a. So to look at the definition of a log, the first thing we need to notice is that we're going to assume that our x values are going to be positive or greater than 0, as well as our a values, and our a value cannot equal 1. If that's the case, then we say that y equals log base a of x. And what we can do is we can rewrite this function as an exponential function where x is equal to a to the power of y. So now if you notice, this x here is actually this x. So I would say x equals, and then it says a, which is the base of the power, that's also the base of the log. And then my exponent of my power, which I have right here, is really coming from this value here. So we can take our log function and write it as an exponential function if we need to. So it says the function is called a logarithmic function with base of a. So this base a is usually kind of like a subscript when you're looking at a log, and we'll look at a few examples coming up here. So again, just to reiterate, logs are really exponents. So for our first example, it says to evaluate f of x equals log base 4 of x, and we want to do this when x is equal to 16. So really, I can rewrite this as y equals log base 4 of 16. And how we're going to solve this is we're actually going to use exponents, because in my head, I'm really thinking that 4 to the power of y equals 16. So what does y equal? And again, I got that because the base of my log is the base of my exponent. So 4 to the power of y is going to give me 16. So hopefully we know that when I take y and I raise it to the second power, we end up with 16. So that means that when we evaluate this log, our y value then has to equal 2. Now for part B, it's very similar. So essentially I have f of x, or I'm going to write y, is equal to log base 5 of 1. So if I go and I rewrite that as an exponent, my base of my log becomes the base of my exponent. So 5 to the power of y equals 1. Well, what can I raise 5 to that's going to give me a value of 1? So that means that y then really equals 0, because anything raised to the power of 0 is always 1. And for our final part here for C, I'm going to rewrite this as y equals log base 3. Now you can write this as 1 over 81 if you would like. So I have 1 over 81. And then what I'm going to do is I'm going to rewrite this in exponential form. So the base of my log is the base of my power. So 3 to the power of y equals 1 over 81. So now you have to say 3 to what power will give me 1 over 81. And actually, I think about this as 3 to what power gives me 81 first. So hopefully we know that y, if I take 3 and I raise it to the 4th power, that's going to give me 81. So if I want it to become the reciprocal, or 1 over 81, then I'm going to have to raise that power to a negative number. So I'd have 3 to the negative 4th equals 1 over 81. So negative 4 is my solution for part C. Now, one thing I cannot caution you enough on is that when you're using your calculator, by default, the log button, and it will just say log on your calculator, that's what we call the common log. So a common log means that it's always a base 10. Now you saw in the previous example, we had different bases other than 10. So later on, we'll learn how to do what we call a change of base. But right now, I just want you to know that if you take the log of a number, so if you type in something like the log of 5 on your calculator, even though it doesn't say it, you are really doing log base 10 of 5 because your calculator has a button on it that says log, but it's assuming, or it is set up that way that it's a base 10 log. Okay, there's multiple logs, like as we've already kind of started to see. I'll show you how to handle those later, but right now, just know on your calculator that does a base 10 log. Now, logs are kind of unique. They have a couple special properties, and if you can memorize them, great, or the more you use them, the more you'll know them, I guess. But these just kind of help you when you're trying to solve log problems. So the first one says that log base a of 1 is going to equal 0, and that's because a to the power of 0 equals 1. If you're taking the log of base a of a, so in other words, if the base of your log is the same as this right here, then that's going to be 1 because a to the first power is going to give you a itself. If we're taking the log base a of a, and we're raising that a to the power of x, essentially what happens is the base of the log and the base of the exponent here, they're going to kind of cancel, and that's going to leave you with just x. Okay, now notice here, if you have a being raised to the log of base a, these are also going to cancel and leave you with x. That's an inverse property. And then the last property that we have says log base a of x equals log base a of y. So notice how these logs have the same base. So because they have the same base, if I want to go and solve, the only thing that's different is this x and this y. So what that means then is I can go ahead and set x equal to y, and then I can solve for whatever value I need to. So let's take a look at the next example, which is going to kind of use some of these properties. So for example 2, we have log base 4 of 1, and we want to simplify this. Well, really, if you think about it, you have 4 to what power is going to equal 1. So anything raised to the power of 0 is going to give me 1. So my solution to this one is 0. Likewise here, we have a base of the square root of 7. So the square root of 7 to what power is going to give me the square root of 7. So the base of my log is the same as this value here. So these are going to kind of cancel, and this is going to become 1. Because the square root of 7 raised to the first power is going to give me the square root of 7. And then last but not least, this was kind of the last property that we looked at. The base of my exponent is the same as the base of my log. So these are going to kind of cancel, and that's going to leave us with 20. For example 3, I notice that we have log base 5 and a log base 5. So because both logs and their bases are the same on the left and the right, that tells me that I can go ahead and set my y, or this value, equal to this value. So right away I can see that y is equal to 16. For part B, I have just the word log written. So if it's just the word log, remember that that's really log base 10, and that would be on the other side too. So because both of these have log base 10s in them, I can now just focus on the 4 minus 3x and the x plus 2, and I can also set them equal to one another. So to solve this one, I have 4 minus 3x equals x plus 2. If I add my 3x to both sides, I get 4 equals 4x plus 2. I'm going to subtract my 2. So this tells me then that x is going to equal 1/2. And last but not least, I have part C. And again, I notice right away that we have log base 3's on both sides, which means I can take that x squared plus 4 and set it equal to 29 so that I can solve. So when I subtract 4 from both sides, I'm left with x squared equals 25. And when I square root both of those, x is really equal to plus or minus 5. Now, one application where you will see logs get used is in chemistry, actually. For those of you that are in chemistry, we'll probably get to this later, or usually at the end of the year. But essentially, it says that you can calculate the pH of a solution using a log function. So if you don't know or don't remember, pH tells you how acidic or how basic something is. So to find the pH, we take the negative log of H3O plus, which is what we call the hydronium ion. So the pH value is a measure of acidity or alkalinity. If we have like pure, like truly pure water, the pH is 7, which is like a neutral value. If you have values that are greater than 7, we know that they are alkaline or basic. If you have pH values that are less than 7, then we say that these are acidic. So for our next example, we're going to find the pH of a solution where the hydronium ion concentration is 2.5 times 10 to the negative 4th. And we want to know if it's acidic or basic. So the first thing we're going to do is we're going to say that the pH is equal to the negative log of that hydronium ion concentration, which is 2.5 times 10 to the negative 4th. Okay, if you type that in on your calculator, okay, I got something around 3.36. So this would be my pH value. Well, because that is less than 7, this tells me that my solution is an acidic solution. Now for part B, we want to find the hydronium ion concentration of a solution with a pH of 7. So here I know, 7.1. So here I know my pH is 7.1. Now I have to find the hydronium ion concentration. So I'm still going to do the negative log of that hydronium ion concentration. And then what I have to do is I just have to solve for it. So the first thing I'm going to do is I'm going to get rid of the negative. So now I have a negative 7.1 equals the log of the hydronium ion concentration. And I'm going to use my properties of logs because I remember that a log is really a base 10. So I can take the base of that log, raise it to this negative 7.1. So if I raise that to the negative 7.1, then that should give me my hydronium ion concentration. So when I do that, my hydronium ion concentration is going to be somewhere around 7.9 times 10 to the negative 8 is what I got when I type that in. Now the last thing we're going to look at today is what we call the natural log function. The natural log function is kind of like a specific case for logs. And what that does, or the only difference is that it's log with a base of e. So it's a log base e of x is actually equal to, and we have what we call ln of x, and ln is really the natural log. So if you see something like the ln of 3, we really know that that's a log base e of 3. So if y equals ln of x, then because I really have, if I were to rewrite this as y equals log base e of x, I can, that's really the same thing as saying x equals e to the y, because if I take the base of my log, so that's e, I raise it to the left-hand side of my equation, and I set it equal to this. Notice that these here are really the same. Now on your calculator, you'll see too that you do have a natural log button. And so natural log is just a log of base E. Notice that the properties for natural logs are the same as the properties of logs. So if I take the natural log of 1, that's really equal to 0, since e to the power of 0 is 1. The natural log of e is equal to 1, because that's really like saying e to the first is equal to e. If I take the natural log of base e, these kind of cancel, and that's going to leave me with just x. And if I take the natural log of x and I set it equal to the natural log of y, because the natural logs are the same, then I can really go ahead and solve for x equals y. So our final example for today says the natural log, or we're going to solve these, the natural log of e to the 1/3. Well, remember, that's like taking log base e of e to the 1/3. So what's going to happen is these are going to cancel, and that's going to leave you with 1/3. Here, for part B, we have 15 times the natural log of 1. So if I rewrite this with my log notation instead of natural log, that's really 15 times the log base e of 1. Well, log base e of 1 is really 0. So this piece here is going to 0 because e to the power of 0 gives you 1. And 15 times 0 then is also going to be 0. For part C, I have e to the natural log of 8. Well, if I rewrote that, that's really e to the log base e of 8. Because my base of my log is the same as the base of my exponent, or my power, I'm going to cancel those out, and that's going to leave me with 8. And then here, I really have log base e of e being divided by 6. Well, again, when I have a log with a base that's equal to the same base of the power, these are really going to cancel and leave you 1. So here, I'm left with a solution of 1/6. Please let me know if you guys have questions. Again, I will be back in class to help you on Monday. I just ask that you please try this stuff. And I hope you guys have a great day, and I will see you soon.